A turtle, a mysterious pattern, and a 4,000-year-old puzzle. What do these have to do with modern AI? The answer might surprise you. Let's decode the amazing world of magic squares. But before we discover its real secret, let's play a simple game. Imagine there is a huge treasure chest in front of you. It can be opened with just one key. The problem is you have 100 different keys. What would you do? You would try one key. It doesn't work. Try the next one. Still doesn't work. You keep trying one key after another until you finally find the right one. When a computer faces a similar problem, it does exactly the same thing. It checks every possible solution one by one until it finds the correct answer. In computer science, this approach is called brute force. It works, it eventually finds the answer, but there is a price. It consumes a lot of time, memory, and computing power. Then someone asked a question that changed computer science forever. Instead of searching everywhere, why not search only where the answer has a chance of existing? That single idea became one of the foundations of modern AI. In AI, these are called constraint satisfaction problems or simply CSPs. But there is another twist. Sometimes a choice looks perfectly correct, but a few steps later, you realize you have reached a dead end. There is no way to reach the goal anymore. So, what do? You go back to the point where things went wrong. Undo your last choice and try a different path. In computer science, this smart technique is called backtracking. Think of it like exploring a maze. Move forward, hit a dead end, go back, try another route. Simple. Let's say you are looking for your friend in a new school. Moment you enter, you ask, "Where is he?" Someone replies, "Try the library." Now, would you still waste time checking every classroom? No. You would head straight to the library because that one clue eliminated all the unnecessary searching. That's exactly how smart computers work. When you play games like tic tac toe or chess, the computer doesn't check every possible move. Instead, it uses smart hints to focus only on the most promising choices. These smart hints are called heuristics, and believe it or not, the ancient Lo Shu Magic Squares helps us understand this idea. Instead of searching through everything, it helps eliminate almost 90% of unnecessary searches. That's why this ancient number puzzle still helping us understand modern artificial intelligence. And that's exactly what we are going to decode step by step in this video. Welcome to the amazing world of magic squares. Now imagine you want to send a secret message to your best friend, but you don't want anyone else to understand it. What would you do? You would convert your message into a secret code. That's called encryption. Your friend receives the message, but it's still in code. To read it, they must convert it back into the original message. That's called decryption. Both encryption and decryption need one thing, a secret key. Just like you need a key to unlock your house, you need the correct key to unlock the hidden message. Without that key, the message makes no sense. Believe it or not, people were using similar ideas thousands of years ago. The sage Vyatsayana described an art called Milechita Vikalpas, one of the famous 64 arts. It literally means secret writing. Anyone could read it, but the only intended person could understand it. Today we call this cryptography. For instance, take the word amla. If you simply rearrange the letters using an agreed rule, only your friend will know what really it means. To everyone else, it's just a random word. That's one of the simplest forms of secret communication. Another method is called object substitution. Instead of sending words, you send an object. Imagine giving your friend an Indian gooseberry. It's not just a fruit, it secretly means get well soon. The object itself becomes the message. We have already seen another brilliant Indian idea in our video on scientific notation. Ancient Indian mathematicians used the Kattapayadi system to hide numbers inside letters. For instance, instead of memorizing the digits of pi, they converted those numbers into meaningful verses or poems. This made the digits much easier to remember while keeping them in the exact correct order. People didn't always use written codes to send secret messages. Sometimes they didn't even use words. One fascinating example is whistle language. In India, there is a place called Kongtang village in Meghalaya, often known as the whistle village. The Kasi tribe communicates using unique whistle melodies. Instead of speaking a person's name, they whistle a special tune. Each tune is different, just like a unique ringtone for every person. These whistles can travel much farther than normal speech. So, if someone is deep inside the forest or standing on a distant hill, a whistle can carry the message much more effectively than shouting. It's a simple yet brilliant way of communicating. Now imagine you are the commander of an ancient kingdom. Your army is waiting at the border. You need to send a secret military message. But if the enemy captures it, your entire plan could fail. So instead of writing the message normally, you hide it inside a square grid. To everyone else, it looks like a normal collection of numbers. Nothing makes sense. But here's the secret, the message isn't meant to be read from left to right. Instead, you read the letters by the following movement of a knight on a chessboard. The knight's path becomes the secret key. Only the person who knows that key can read the letters in the correct order. And suddenly the hidden message appears, attack at midnight. Without the key, it's just random letters. With the key, it's a secret military command. That's the basic idea behind cryptography. The secret isn't hidden, the way you read it is. The story of the world's most famous magic square begins nearly 4000 years ago in ancient China. According to an ancient Chinese legend, a giant turtle came out of the Luo River. People noticed a strange pattern on its shell. That the pattern of dots on its shell wasn't random. It formed a strange and fascinating arrangement like this. Many people believed this mysterious pattern carried a hidden meaning. Over time, that pattern became known as the Lo Shu Magic Square. Now we don't know whether this legend is historically true, but one thing is certain, the Lo Shu Magic Square became one of the most famous mathematical pattern in human history. Its journey didn't stop in China. The idea spread across the world to India, Persia, the Arab world, and eventually Europe. Mathematicians from different civilizations studied it from different perspectives. Some admire its beautiful symmetry, some explored its mathematical properties, others discovered entirely new ways to build magic squares. Now, let's travel to India. One of the greatest mathematical genius the world has ever known, Srinivasa Ramanujan, was also fascinated by magic squares. He even created a remarkable magic square using his own birthday. But he didn't stop there. Ramanujan wanted something much bigger. Instead of creating just one magic square, he searched for a general mathematical method that could generate countless new magic squares. And that's where the story becomes even more fascinating. Think about Lego blocks. The blocks themselves never change, but depending on how you arrange them, you can build a house or a car. The same thing happens in a magic square. The numbers don't change, only the arrangement changes. That's the real secret. A magic square isn't about the numbers, it's about patterns, logic, and balance. So, let's build one from scratch. First, draw a 3 by 3 grid. Now, add one extra row at the top and one extra column on the side. These are called the outer grids. We will only place the numbers 1 to 9 inside the main 3 by 3 grid. And yes, there are a few simple rules. The gamma move. Every new number follows the Greek capital letter gamma movement. That means move one cell up, then one cell right. Notice, this is not a diagonal move. It's two separate moves, first up, then right. Every new number follows this same pattern. Wrap around. What if your gamma move takes you outside the grid? Simple. The number wraps around and comes back from the opposite side. Think of the grid as a sheet of paper. Now roll it into a tube. If something goes out from the right side, it comes back from the left. If it goes out from the top, it reappears at the bottom. This is called the wraparound rule. It's not just a trick, it's actually a beautiful geometric idea. There is one more rule. If the destination cell is already occupied, don't make the gamma move. Instead, place the next number directly below the last number you wrote. That's it. Just three simple rules. Now, let's build the magic square. Start by placing 1 in the top middle cell. Now, make a gamma move. One step up, one step right. The number 2 goes outside the grid. So, we use the wraparound rule and bring it back from the opposite side. Now for 3. Again gamma move. It goes outside the grid, so wrap it around. Now the destination is already occupied by 1. What do? Easy. Skip the gamma move. Place 4 directly below 3. From here 5, 6. Follow the same rules. When you reach 7, you will again hit an outside grid. So place 7 directly below 6. For 8, make the gamma move. It goes outside, wrap it around and place it. Finally, place 9 using the same rules. And just like that, your 3 by 3 magic square is complete. Here's something really interesting. Why did we start with 1 in the top middle? Could we start somewhere else? Absolutely. You can start in different positions. Using rotation and reflections, you will still generate the same family of magic squares. For example, the ancient Chinese Lo Shu Magic Square places 1 at the bottom and 9 at the top. Why? Because ancient Chinese used a different directional system. The emperor traditionally sat facing south. So their maps were oriented differently from ours. In their symbolism, 1 represented winter, 9 represented the peak of summer, and 5 sitting at the center represented balance and harmony. So the Lo Shu Magic Square isn't just mathematically beautiful, it's also deeply connected to ancient Chinese culture. Think of a Rubik's Cube. You can rotate it, flip it, or look at it from another angle. Its orientation changes, but it's still the same cube. A magic square works exactly the same way. Rotate it, reflect it, change its orientation, the appearance changes, but mathematically it's still the very same magic square.